Hello, I'm Mori, Assistant Professor from Gargi Memorial Institute of Technology. So today we are already started our next lecture on a laser. So today we are try to develop a equation of Einstein AV coefficient and the transition probability for the laser. Okay. So what is, first of all, what is AV coefficient for the properties of the laser? In the last lecture we are already know that what is spontaneous emission, stimulated emission, stimulated absorption. Okay, so let let us calculate the rate of transition between two energy state energy state 1 and 2 having energies E1 and E2. Okay, so first of all it is needed for the stimulated absorption. Okay, the probable rate of absorption is, so obviously this is a E2, this is the E1 state, so one electron lies in here. When you insert a photon from the outside, this energy is taken by this atom and it is going to the lower state to the higher state. This is the spontaneous absorption. Okay, uh, let let the energy density CT is written by U is a function of nu. Energy density is a function of frequency incident on the atom. The energy density is defined as radiant energy per unit volume in the range of frequency nu and nu plus d nu. So the energy density is defined as the radiant energy per unit volume in the range of frequency nu and nu plus d nu. Okay, so the now the probable rate of absorption is given by P 1 2 is proportional to U nu, or P12 is equal to B12 is into u nu. So what is that? It shows that, so we are already draw a diagram for the stimulated absorption. The stimulated absorption is depend on the how much energy have this outside photon. Okay, so suppose the energy density of this photon is u nu, then the probability rate of absorption of this energy, of the energy of this outside photon, is the probability of absorption is proportional to the energy density. That means the energy density, if you increase the energy density of this photon, then the obviously absorption rate or absorption probability is also increases. That means the absorption probability is always proportional to the energy density of this photon. That means P12, because the transition is done from 1 to 2, because the atom is getting the energy from this photon and going to the first lower energy state E1 to E2. That's why from 1 to 2, from state 1 to 2, that's why we written here in a suffix P12 is proportional to u nu, and the proportionally constant is also is written as a B12, because the transition from first state 1 to state 2. That's why we written here 1 to 2. That because when the atom get the energy from this outside photon, and this atom is excited and jump from state 1 to 2. That means the transition from state 1 to 2. That's why I written here P12 equal to B12 u nu. Okay. So this B12 is proportionality constant, is also known as Einstein coefficient. Einstein coefficient. Okay, this is the first case, and the second case is spontaneous emission. Now the atom is already excited by the stimulated absorption. So now the atom already is in a excited state. So that means in this condition, this atom again return to its initial state. When this atom is coming back to this initial state, this atom release the extra energy in term of h nu. This is known as spontaneous emission. So that means the probability of spontaneous emission 2 to 1 so the spontaneous emission. So due to the stimulated absorption, the already this excited atom already situated in a excited state 2. So for the instability, this atom again return to its initial lower energy point or energy state E1. So this process is known as spontaneous emission. Okay. So spontaneous emission, the probability of the spontaneous emission from state 2 to 1, from state 2 to 1, the probability spontaneous emission. Okay, this is okay denoted by A21, known as Einstein coefficient of spontaneous emission of radiation. So that means this A21 is denoted by the probability of the spontaneous emission rate. Probability of spontaneous emission, that means P21 is equal to A21, because this transition is from second state to first state, so that's why we written here in a suffix 221 is denoted by 221. Okay, and another thing is that this P21 P, the probability from second state to first state is not dependent on the energy density, because this electron, this atom already is situated in a excited state. So that's why no external energy or energy density is not responsible for the transition of this atom from energy state 2 to energy state 1. That's why this is directly equal to the coefficient of the spontaneous emission. This is the coefficient of the spontaneous emission. Actually the probability is proportional to the probability of the transition from E2 to E1 is always 1. That means P21 is always proportional to 1. The probability is 1 equal to. So when you equalize this one equal to that coefficient, actually the probability for the spontaneous emission is always equal to P21. And now the third case is known as stimulated emission. Stimulated emission. So it is stimulated emission. It is done by E2 to E1 h nu. Due to this h nu, the external h nu gotten by this atom and jump to the higher energy state. And for the instability when so when you insert some atom already situated in a excited state E2, and when you put some external energy from the outside, due to this external energy this atom again return to its initial state. That means the 2h nu is getting out from this whole transition, and this method is known as stimulated emission. And the transition, the probability, in this case the probability of stimulated emission transition two to 1 is proportional to U nu or energy density, because this external energy is excited this E2. That's why the E2 is jump from E2 to E1. That's why the 2h nu is exit from this whole transition, and this method is known as stimulated emission. And P21 is equal to B21 U nu, where B21 is known as Einstein coefficient of stimulated emission. That means the in the case from case 2 and 3, we get P21 is equal to A21 plus B21 U nu. This is for the spontaneous emission, this is for the stimulated emission, and this is the whole transition of second state to first state. Okay, so now we try to develop a relation between Einstein's coefficient. So you already get the three coefficient of Einstein: B12, A21, B21. Okay, let N1 and N2 be the number of atoms in E1 and E2 state respectively. So later we think that the E1 state occupied by the N1 number of atoms, and E2 state is occupied by the N2 number of atoms. Okay, now from equation we already have P1 is equal to B12 U nu. Now N1 P12 is equal to N1 B12 U nu. Suppose this is the equation 1. Okay, again we have P21 is equal to A21 plus B21 U nu, or N2 P21 is equal to N2 A21 plus B21 U nu. This is the equation 2. Okay, so under the equilibrium, N1 P12 is equal to N2 P21. The probability of the total number of atoms in a first energy state, that is defined by the how many number of atom is going from energy state 1 to energy state 2. This is signified by the how many number of atom is going from energy state 1 to 2, and this is signified the how many number is coming from the energy state 2 to energy state 1. So under this equilibrium the total mathematical values are equal. So when I put the values B12 U nu, or N2 A21 plus B21 U nu, or N1 V12 U nu minus N2 B21 U nu is equal to N2 A21, or U nu is equal to N1 B12 minus N2 B21 N2 A21, or U nu is equal to N2 A21 whole divided by N1 B12 minus N2 B21, or U nu is equal to A21 by B21 dot 1 by N1 by N2 dot B12 by B21 minus 1. We divided the upper term and lower term by the N2 B21. Clear? just divide it by B21 and we get this. We get so it is clear for everyone. Okay, this is the nu coming in term of coefficient, Einstein coefficient, and the number of atoms in the system. Okay, so now dynamically the stimulated absorption and stimulated emission is equal. That means how many number of absorb the external energies, that number of atoms again for the stability is coming over to the energy state 2 to energy state 1. So that means the stimulated absorption is equal to stimulated emission. So we can rewrite that B12 is equal to B21. Now U nu is coming over that A21 by B21 into 1 by N2 by N1 is equal to B12 by B12 minus 1. We putting B21 as a B12, A21 by B21, 1 by N1 by N2, N1 by N2 minus 1. So suppose this is the equation 3. Now according to Boltzmann distribution, law, we know that N1 by N2 is equal to exponential over E2 by E1 by KT, or exponential over H nu by KT, because E2 minus E1 is denoted by H nu, where now from equation 3 we can rewrite that U nu is equal to A21 by B21 dot 1 by exponential over H nu by KT minus 1, and we are already set up this equation in a statistical chapter, the application of the B statistics. We putting here, rewrite here actually, according to the Planck's radiation law, we know U nu is equal to 8 pi H nu cube by C cube 1 by exponential over H nu by KT minus 1. This is suppose equation 4. So is equation 4, this is equation 5. Now compare equation 4 and 5, we get A21 by B21 is equal to 8 pi nu cube, 8 pi H nu cube by C cube. This is the relation between A21 and B21, the coefficient of Einstein. Two types of coefficient of Einstein, the spontaneous emission coefficient and the spontaneous emission coefficient and stimulated emission coefficient. Ratio is defined as a 8 pi H nu cube by C cube, where is C is the speed of light in a vacuum. So this is the relation between Einstein coefficient. Is it clear for everyone? So in this lecture, first of all when we started from the Einstein, we try to develop the Einstein AV coefficient. What is Einstein AV coefficient? We first of all get the three transition process of atom in a laser. First is stimulated absorption. Thus in a stimulated absorption, obviously the probability of the how many number of atom is going from energy state 1 to energy state 2, it depend on the external energy. So P12, the probability is proportional to U, and P12 is always equal. When you put equal sign, you somewhere put the probability constant, and we are putting here B12, and B12 is defined as transition from one state to second state. Okay, then the second process is stimulated emission. There is a probability is only depend on the how many number of atoms is already situated in a equilibrium state, because in a spontaneous emission we does not need of any external energy. That means the P21 is in the case of the spontaneous emission is not depend on the external energy. So P21 is always equal to, proportional to 1, because the number of atom is excited in an excited state. So the whole number of atoms is coming to the excited state to the lower state. That means the second state to the first state. That means 2 to 1. And the case of the third case, the stimulated emission, so obviously it is depend on the external energy. So when you put some external energy from the outside, then the excited atom get some triggering energy, that's why when this atom is get triggering energy, then this atom is coming from E2 to E1, then we get a 2 H nu. In that case we get the multiple number of H nu. So this is the stimulated emission. So in this case P21 is proportional to U nu, and the proportionally constant is B21, because of the transition from second state to first state. So total transition from second state to first state, the total transition from second state to first state is defined by the P21 is equal to spontaneous emission part and the stimulated emission part. This is the total emission part, and this one is the total absorption part. Okay, then we just multiply with the probability with the n1 in the both sides, in the both two equation, because the probability is only depend on the how many number of atom is going from first state to second state or second state to first state. So in the equilibrium, the probability and the number of atoms in the both state is always equal, because how many number of going from first state to second state, and the same number of atom is coming from the second state to first state. Then we just equate these two equation and simplify this one. We get this one in form of U nu. U nu is the energy density. And the thermodynamically we know that the stimulated absorption and the stimulated emission is always equal. That means how many number is going to the first state to second state, and same number of atoms is coming over from the second state to first state. That means the coefficient is equal. Then we put the value of the two coefficient is equal and simplify this one. U nu is term of U. According to the Boltzmann distribution law, because we taking over atom as a, in the case of the laser, we taking the atom as a gas molecule. That's why we use the MB statistic, and the Boltzmann MB distribution law is written like that: exponential by E2 minus E1 by KT. E2 minus E1, the transition of energy value of E2 minus E1 is defined by the H nu, the external energy. So just putting the value of the N2 by N1 is exponential H nu by KT from the Maxwell distribution law. Then we compare this equation with the Planck's radiation law, because in the laser the energy is released from the ultimate transition. This whole energy is a radiant energy, because laser light amplification of the stimulated emission by radiation. So whole energy is radiated in form of light energy. So we use the Planck's radiation law and compare these both equation. We get the A21 by B21 ratio in form of 8 pi H nu cube by C cube. This is the Bose-Einstein coefficient, AB coefficient. Okay. Okay, thank you. In the next lecture, we try to uh, develop the we try to understand the what is coherence of the light, and we try to find out the Q factor of the laser beam. Then we shifting over some example of the laser like helium ni- helium helium neon laser, ruby laser, semiconductor laser. Various example we have, which type of laser we have, and what is the mechanism of such type of laser is done in between the transition of the atom in that type of laser. We study about some specific example in our according to our syllabus. Okay, thank you.